So are we live or?
Yes, we are live now. You can start.
Okay. Welcome back, everybody. So welcome to lecture 9. So we'll continue our discussion on spectral expansion. So what I thought I'll do last lecture, I thought I was a bit fast. So I thought I'll give a quick recap of what we did last lecture and then continue on how the second eigenvalue of the spectral gap talks about the random mixing of the underlying graph. So let's recall some of the notation we built last time. So we wanted to understand the random walk on expander graph. So for that in particular, we took any graph, not necessarily regular, looked at the adjacency matrix of that graph. We defined this random walk matrix, which is MD inverse A. D is the diagonal matrix, which has the degrees on the diagonal. And the adjacency matrix is the symmetric matrix that you're familiar with. And this what's the nice property about this matrix is the UVth entry of this matrix represents the probability that you go from U to V. If you're at U, what's the probability that you'll go to V? If it exactly represents this probability. When you're going by the random walk, in which at every vertex you go choose one of its neighbors equally at random. So at a vertex U, you have degree U choices. You pick one of them at random and go to one of them. So that's the random walk matrix we are talking about. And we saw that this matrix we view this matrix both from the view of right multiplication, in which case it was this random walk matrix. It was taking a probability distribution on V, it would just transform it from P to P transpose in this one. So this sort of represents the random walk as T proceeds. And we also saw that there is a nice stationary distribution for this walk. The distribution which is proportional to the degrees is the stationary distribution for this walk. So in particular, it has this property pi transpose M is pi. This is what right multiplication gave for us. By the way, this is just a recap of last lecture. So do stop me if anything was, you need ask me, have any questions from last lecture. So I'm just going over a quick survey of everything we did last lecture. So this is right multiplication. Then we also defined what left multiplication is. It took a vector on the vertices and sort of did an averaging operator. It was viewed as an averaging operator. We viewed it as an averaging operator. And in this case, the all ones was sort of the left eigenvalue for this matrix. So based on these two, we came up with this. We defined this notion of an inner product, which is almost the usual dot product, except, so it's almost like the usual dot product, except that it is scaled by this pi u. So it's just FU GU, it's an inner product on RV. So it's an inner product on. And if you're more familiar with the matrix notation, this inner product, so this is U in P. This inner product is just this quantity F transpose. The usual dot product is just F transpose G. And this is just, you're sort of scaling every entry by the stationary distribution F transpose pi G, where pi is the diagonal of there's the diagonal matrices where the diagonal entries are the probabilities given by the stationary distribution. Okay, so that's the inner product. And the key property we noticed of this inner product is the fact that this random walk matrix is self-adjoint with respect to this inner product. In other words, FMG is equal to MFG for all FG. And this fact that it was self-adjoint, the spectral theorem implied that it has an Eigen Basis. Basically, you have vectors, you have orthogonal vectors v1, v2, vn. These are what we call eigenvectors in R. It's an orthonormal basis. So Vig, Vj is, if I not equal to j, Vi and Vj were orthogonal according to this inner product. The vectors were of unit length. The vectors were of unit length according to this inner product. And furthermore, these vectors were eigenvectors. That is, MVi was equal to lambda I Vi. So you had this nice orthonormal eigenbasis because of the fact that M is self-adjoint for this inner product. and it's this inner product. Right? So it might drop out pi at times, but yeah, it's the inner product. So you have this eigenbasis v1, v2, vn, and the corresponding eigenvalues are 1, lambda 2, all the way up to lambda n, and these are sandwiched between 1 and -1. Okay. So I wanted to do one more thing, just given that we talked about this inner product in its matrix notation F transpose pi g, this will come useful for us. So Fg was, so this inner product is F transpose pi g. This is not something which we did last time, but it's easy to see this, that this is in the matrix notation. This is what this one is. So I'm going to write this self-adjoint condition in the matrix notation. So what does Fmg pi mean? Just writing that in this word, it just says F transpose m pi mg. I'm just rewriting this over here. Similarly, mf g pi, this is F transpose m transpose pi g. So this condition is satisfied for all fg in RV. This would mean that pi m, because this is true for every eg. In particular, I could set f to be, it's particularly true for every f and g. I could set f to be ei and g to be ej, the unit vectors. And you would get that the ijth entry of pi m is equal to the ijth entry of m transpose pi. Therefore, as matrices, these two things are equal. And the only reason for my doing this is I will use this later on in today's lecture. That this matrix M has this property. No, if you stare at this, is just stating that A is a symmetric matrix. It just follows out of that. So pi M is equal to M transpose pi. Okay. Okay, all of this was just setting up notation. The first important theorem which we actually proved was this, what we call as the expander mixing lemma. Expander mixing lemma says that if you're given M, which is a random walk matrix with spectral gap 1 minus lambda. So what was spectral gap? Did we define spectral gap over here? I didn't define spectral gap, so I didn't write the so spectral gap of a matrix is this is the minimum between 1 and lambda 2 and lambda n and -1. So that is spectral gap. That's how we define spectral gap. So it's basically, if you view the eigenvalues lined up on between -1 and 1. So it's lambda 2 is over here, lambda n is over here. That's 0. It's this minimum gap is what we call, that gap is the spectral gap. Okay. And we then went on to prove what's we call the expander mixing lemma, which says the following property. If M is a random walk matrix with spectral gap 1 minus lambda and stationary distribution pi. Now let S and T be any two sets of subsets of vertices such that their corresponding weight mass according to the stationary distribution is alpha and beta. Now pick a random edge on this according to the random walk matrix. The probability that the left endpoint is in S and the right endpoint is in T. If you look at this probability, minus alpha beta, in which you pick the two endpoints completely independently at random, not according to the random walk, completely, that would be alpha beta, says that the difference between these two objects is not, these two probabilities is not too large. It's lambda times square root alpha into 1 minus alpha, beta 1 minus beta. This is an immediate consequence of the fact that we have an eigen basis for the random walk matrix. Okay, this was what we did. And then when we applied the expander mixing lemma to a set S and T being the non-neighborhood of the complement of the neighborhood, we got this theorem. We got this theorem which shows that anything which has spectral gap is actually a vertex expander. This was where we concluded last lecture. This was the lecture. This was the statement which we had. It was stating that spectral expansion implies vertex expansion. The spectral expansion is This was the last thing which we did. So let's recall this. If you have a graph G with spectral gap 1 minus lambda, then the graph is actually a row n comma 1 by lambda square plus 1 minus row lambda square vertex expander for all row. For every row between 0 and 1, this is a vertex expander with the corresponding vertex parameter, with this corresponding expansion parameter. And the thing to notice is this quantity, as long as rho is less than 1, because lambda is greater than 0, as long as rho is less than 1, this quantity is a number which is strictly larger than 1. Therefore, every set of size smaller than which is not the full set does expand by some factor or the other. That's what this is stating. So this was where we concluded last time. So I just give a quick summary of what we did last time. Any questions so far? This is everything which we did last time. What we will do is we'll now take this and discuss this for a while and then talk about how the theory we have built so far will imply that these walks mix well. Questions? So just rewriting as this obvious corollary of this one. So this, I think Ishan asked this question about, which I just expanded on, that notice that vertex expansion, we just give a particular set, all sets of size up to k expand by a factor a. But spectral expansion, once you have spectral expansion, you get that every set of every size expands. Of course, the amount it expands by depends on the size of the set. Smaller sets expand better than larger sets, but every set, as long as this row is bounded away from 1, you do get some expansion factor or the other. It's not like only small sets expand. If you have spectral expansion, every set of every size expands. As long as the size is bounded away from 1, that set expands. I'm just writing this corollary of this one. So if G is a deregular graph on n vertices with spectral gap lambda, I'm just setting rho to be half, we get that it is a n by 2 comma 1 plus delta vertex expander for some delta greater than 0. Okay. So this is fine. So this says vertex expansion implies spectral expansion. What about, is the other direction true? And surprisingly, the other direction also happens to be true. This we will not prove. Surprisingly, the converse is also true. Just like the expander mixing lemma had a converse, the converse is also true. More particularly, I mean the following statement, that if you have vertex expansion, then you also have spectral expansion. More precisely, for every delta greater than 0 and d greater than 0, there exists gamma. There exists a gamma which is gamma. This is a lambda greater than 0, such that if G is a deregular n by 2 1 plus delta vertex expander, then G is a gamma spectral expander. And in particular, we can say take, sorry, not gamma, 1 minus lambda spectral expander. And we can take lambda to be something like omega delta by t square. Forget about what this theorem says, what this quantitative, forget about quantitatively what it says. What qualitatively what it says is, if a graph is a vertex expander and sets of size up to n by 2 do expand by a factor larger than 1, then the graph, you can show there's a spectral gap, and the spectral gap is a constant independent of n. That's the important thing to state. So if you put these two together, this is the sort of conclusion we have, that the following two statements, that is, let G be a family of deregular graphs an infinite family, then the following two are equivalent. One, there exists a constant delta greater than 0 such that G is a n by 2 1 plus delta vertex expander. There's a constant lambda greater than 0 such that G, such every G in G is a 1 minus lambda spectral expander. All I'm claiming is these two statements are sort of loosely equivalent. That is, if I can prove spectral expansion, we saw how it implies vertex expansion. This is what we did towards the end of last lecture. And I stated without proof, the converse is also true, that if it's a vertex expansion up to sets of size n by 2, then it implies spectral expansion. So because of this equivalence, then we won't specify. Typically it's common this practice not to say if a graph is a spectral expander but a vertex expander. They will just use the word expander loosely and to mean, and it remarks to one of this. Just an expander means all sets of size at least n by 2 do expand by some factor greater than 1, or the fact that there is a spectral gap and the gap is larger than 0. Okay, so this one I should put lambda less than 1. This is 0 less than lambda less than 1, such that this is a spectral. That's what these two properties. So these are sort of equivalent properties. Is this fine so far? But what I want to impress, what we'll take the next 5 minutes or so to say, this is only there's a qualitative equivalence between these two notions. So there's a notion of spectral expansion, there's a notion of vertex expansion. These are two notions of expansion. One is vertex expansion is talking as a combinatorial notion, which is talking about how much do sets of a particular size or sets of size up to a particular value expand by. That's vertex expansion. It's a combinatorial property. Spectral expansion is a more analytic property. It's the gap between the second largest eigenvalue and 1 and the least eigenvalue and -1. It's the minimum of these two gaps. That's a spectral gap. And what we're seeing is these two things qualitatively imply each other. If there is a spectral gap, then the corresponding graph is a vertex expander. If the graph is a vertex expander up to sets of size n by 2, then it's also a spectral expander. We can ask how tight are these convergence. That is, you go from, in this theorem, you go from this delta, you get a gamma. you get a lambda, you get to lambda. Then from lambda, you go back to delta. Is there a loss of parameters when you do this? You can ask this. This is something which we can ask. And this is, so what I want to say is actually, this is only a qualitative equivalence between these two. When you go back and forth, there's a quantitative loss in parameters. The best spectral expander, we don't know how to get it by taking a vertex expander and converting and then stating that this will be the corresponding eigenvalue. And similarly, the best vertex expander, we don't get it from taking a spectral expander and seeing what's the best vertex expansion for it. And I want to say this equivalence between them is only a qualitative equivalence. It's not a quantitative equivalence. If you actually want to know what's the best gap, you won't, for the best gap in the spectral case, you don't get it by actually getting constructing a vertex expander of which expands best and constructing the corresponding spectral gap for it. And similarly, the other way around. This is only, it's a qualitative equivalence between these two notions of expansion up to constants. As long as you don't care what the gaps are, what the expansion is, as long as it's some constant, then they are equivalent. Otherwise, there's a loss of parameters going from one to another. By the way, I've been speaking for 20 minutes and I haven't had a single response. So you guys can hear me?
Yes.
Yes.
Yeah. Okay.
I have a question. So is the n by 2 here particularly important, or can it be like something lesser than half?
So it cannot be lesser than half. So half is important. No, first, let's look at this. So why is half important? So spectral expansion, we saw it gave it up to every, not just half, it even gave all the way up to 1.
Yes.
So corollary of that was even sets of size n by 2 expand. Now, yes. suppose I take a graph which has, I take two disjoint graphs, which are both vertex expanders, and I put them beside each other. That's also going to be a vertex expander for sets all the way less than n by 2.
Right.
Now, this is certainly, it doesn't have a spectral gap because the second eigenvalue now.
Okay, that is, yeah,
that's the reason why. So that's the counterexample to it. So you'll need at least sets n by 2 to expand. And it says that you don't need anything more. Once you get n by 2, you get the whole thing. Yeah. Okay. That answers your question, Sushant. No?
Yes.
Yeah. Okay. So now what I want to know is, now let's ask qualitatively, what is the best? So qualitatively, when I go from spectral to vertex, expansion, what did we got that if G is a 1 minus lambda spectral expander, then G is a rho n 1 by lambda square plus rho 1 minus lambda square vertex expander. Now let's stare at this one. We know that this quantity can never be larger than D. A vertex expand, if it's a graph is a deregular, let's focus our attention on deregular graphs. So if G is deregular, deregular, 1 by lambda square plus rho into 1 minus lambda square has to be less than D. It cannot be larger than D. The expansion can never be larger than D. In fact, we mentioned that it can't be larger than D minus 1 also in the first lecture on expansion. So in particular, if you think of sets of very small size, rho tending to 0, this will tell you that lambda square has to be at least 1 over square root D. So the second eigenvalue, so the lambda square, therefore this tells you that if you look at second eigenvalue, lambda square is, you have 0, this is, you have that all the, this is lambda is this, it's a bound on the absolute value between the second eigenvalue. It says that this has to be at least 1 over square root D. It cannot be smaller than 1 over square root D. That is, the smaller the second eigen lambda, the better is the spectral expansion. It says if you're working with deregular graphs, you cannot hope to get lambda to be smaller than 1 over square root D. In other words, you cannot get sorry, this is when I didn't mean lambda, I meant, what do I mean over here? So lambda should be larger than 1 over d, lambda square, that is lambda should be larger than 1 over square root d. Are people okay with this so far?
Absolute value, right? Absolute value. Absolute value of lambda is greater than 1 by root.
Yeah. Lambda is lambda is always a number between 0 and 1. Lambda is a number between 0 and 1. Yeah. So lambda is greater than 1 over square root d. So the spectral gap cannot be larger than 1 minus 1 over square root d. Okay, it says that. But actually, so this is theorem says that no. So what am I trying to say? The best vertex expansion is something which has vertex expansion d. And now this is stating that if, because we have spectral expansion implies vertex expansion, this lambda which you got from this one cannot be too small. The smaller it is, of course, the better is the vertex expansion. It cannot be too small. If the graph is d-regular, it can only be 1 over d. It cannot be smaller than 1 over d. But actually, this is not the best bound you can get. You can actually improve this bound. This is a statement due to Alone and Bopanna. So let G be a family, an infinite family of d-regular graphs. So it's an infinite family, but all the graphs are all d-regular. With spectral expansion 1 minus lambda. So they all have spectral expansion 1 minus lambda. Then lambda of the nth vertex in this family is greater than or equal to 2 by square root d minus 1 by d minus an order n1, where order n1 goes to 0 as n goes to infinity. So this is a slight improvement of what I had said previously. Previously, I said lambda has to be greater than 1 over square root d. This says it's more like greater than 2 over square root d. So you can get a slight, this is a, all I'm claiming is that there's a slight, you can slight improvement on this. Lower bound for lambda. So result of Alone Bopanna. It's not a hard theorem, but we will not prove this. We won't need this. It's not a hard theorem. So once it says that you can never construct spectral expansion smaller than in which the lambda is smaller than 2 over square root d, rather 2 over square root d minus 1 by d, 2 over square root d minus 1 by d. That's the best you can construct if you want an infinite family. By the way, if you didn't want an infinite family, if you want a specific graph, there's an obvious counterexample to this. And can you guys see where I want a particular d-regular graphs. What's the smallest lambda you can construct? So let's take the complete graph on d plus 1 vertices. This is a d-regular graph. The complete graph on d plus 1 vertices is a d-regular graph. What are, we didn't spend time looking at its eigenspectrum, but do you know what are its eigenvalues?
I mean, you mean the one with self loops, right? On each.
Yeah, I mean, so then the graph on d vertices with self loops, yes. Okay, this particular graph happens to have, if you look at it, the graph with what the graph with Ram Prasad is talking about, it is a graph on d vertices. It's a complete graph on d vertices, but I also have self loops. Every vertex is connected to itself also. Notice what's the adjacency matrix for this? It's the all ones matrix. It's the all ones matrix. This is a rank 1 matrix. Huh? So in particular, it can have only one non-zero eigenvalue. It can't have more than one non-zero eigenvalue. And that particular eigenvalue is we know certainly any adjacency matrix has one eigenvalue, which is the all ones, this one. So that's the only eigenvalue. All other eigenvalues are sitting at 0. So this is a matrix in which the spectral gap is in fact maximum. The spectral gap is 1. The complete graph has spectral gap 1. Yet it's not a counterexample to this theorem which I have mentioned here. And can people say why it's not a counterexample? Do people follow what I'm saying, or I have lost people?
So you want infinitely many graphs, but D is fixed. That is,
so that's the whole point. So what's Abhishek saying? So I gave an example of a particular graph for which it is deregular. It has spectral expansion 1. There is no and it has spectral expansion all the way up to 1. There is no lower bound. So this basically this theorem says the spectral expansion, there's a bound on it. It cannot go all the way to 1 because lambda is lower bounded from below. This number can't go to 1. But the complete graph actually does have spectral gap 1. And why is it not a counterexample to this? It is just one fixed graph. If you give me D, there's only one graph of this type. It's not a family of graphs. If you give me an infinite family of graphs, this says that no, this cannot happen. This cannot happen. As n becomes larger and larger, this gap moves away from 1. And how much does it move away from 1? This is the quantity. So this minus when 1 is sort of absorbing that what happens for this special case for the deregular, for the complete graph and D vertices. But if it's larger, this number will become 0 and this will become the dominant term. Lost people or people with me? And surprisingly, there's an why is this an important statement? There's an accompanying this one, just like in the case of random graphs. In the case of vertex expansion, we said that if you pick a random graph, it's a good vertex expander. Actually, the same thing is true for random graphs. If you pick a random graph, you can ask how good is it as a spectral expander. This was a theorem proved by Friedman. Show the following, that is for any constant D. This is a positive integer. Any constant D, say greater than 3. Equal to 3. If you pick a random deregular graph, on n vertices, then G is a 1 minus lambda spectral expander where lambda of G, lambda is less than or equal to 2 square root D minus 1 by D plus order n1 with high probability. Where once again order n1 goes to 0 as n goes to infinity. So this is the reason why the Alon-Bopanna result is important. Alon-Bopanna says you cannot make the second eigenvalue smaller than a particular this one, and Friedman's results state that you can almost get that. Just pick a random graph, it will have this property with very high probability. It will be almost this one. So this tells you that lambda G has to be larger than this quantity, and this says the random graph will be smaller than this. Of course, there's a smaller one there's a order one n1 term over there. If you, as long as you ignore that, it says these two are a random graph is almost satisfies the Alon-Bopanna bound. So the Alon-Bopanna says you cannot do better than this, and Friedman's result says that if you pick a random graph, you almost get what Alon-Bopanna guarantees. And in fact, so because of this, subsequently we will see, Ramprasad will mention this. So Lubotsky, Phillips, and Sarnak gave an explicit construction of deregular expander graphs for certain Ds, not all Ds. We'll get into that in the next lecture. And furthermore, these have the property that satisfying lambda G is less than or equal to 2 square root D minus 1 by D. There's no additional order n term. They managed to get this. They actually constructed this, and graphs which satisfies this property are called Ramanujan graphs. They constructed Ramanujan graphs, which beats the random construction and it comes even closer to satisfying the Alon-Bopanna bound. These are what are called Ramanujan graphs, and Lubotsky, Phillips, Sarnak actually gave an explicit construction. We will see this explicit construction without proof in the next lecture. We'll actually see what the graph is, but we'll give an alternate explicit construction of expanders, which is not necessarily Ramanujan. Any questions so far?
Can you again explain the thing about infinite family of graphs in the Alon-Bopanna theorem?
Alon-Bopanna bound. So notice the Alon-Bopanna bound is an improvement of this trivial observation that we saw. We saw that if you give me a graph which is an expanding graph, then in particular lambda square has to be larger than 1 over D. This,
yeah,
in which lambda is greater than 1 over square root D. Alon-Bopanna said that you can actually get an improvement of this. That is, if you give me a graph which is an expander, you can actually put a better bound than 1 over square root D. You can put a bound of 2 over square root D. This is roughly 2 over square root D. It's a better lower bound.
Yeah.
But if the family is an infinite family, that is, you give me an infinite family of deregular graphs, and you guarantee that all of them have spectral expansion, then it can't be the case that all the graphs have spectral expansion smaller than 2 square root D minus 1 by D. They will be, after a particular point, it will begin having the lambda will become larger than this value.
Oh, okay.
So it says,
okay,
give me an infinite family, so there will be because this order n1 term will sort of begin coming in. So for the first few graphs in this family, possibly this order n1 term is so large that this doesn't mean anything. But soon afterwards, this goes to 0, and you will say that after a particular point, the lambda will be at least 2 square root D. So this is why the complete graph is not a counterexample, because that's one specific graph. It's not a family of graphs.
right, okay. And what is a family of graph? I mean, it's just a set of with increasing number of vertices, and satisfying this property.
It's just a family of graphs it's just a set of graphs with larger and larger number of vertices.
Okay, it can be arbitrary as long as it satisfies this property.
Yeah, it could be arbitrary. There could be gaps. That is, it could be the first graph is on 1,000 vertices, the next is on million, and so on. Because it's an infinite family, it will have to become larger and larger vertices. It need not be for every n.
Okay, and can you compare this result to the theorem right after this, which was a high probability statement?
Yeah. So this theorem states that take any infinite family, it has this property. Now the next theorem says, let's pick the infinite family in the following way. Let's say D be some constant greater than 3. And let's pick for every n a random graph which is deregular. And let's look at this infinite family.
Okay.
And it says this infinite family with high probability has this property.
Okay.
So it says that this one says that any infinite family, eventually lambda will become larger than this. This says that even if you pick one, the infinite family with this one, it almost comes close to this bound. So these two bounds are more or less tight. You cannot improve. This is what any infinite family, the first bound says that any infinite family will have this property. The next bound says that even a random infinite family comes very close to satisfying this bound.
Okay, almost tight. Okay.
Almost tight. Almost tight. And but this is a random construction. So in that sense, it's not satisfactory. Lubotsky, Phillips, and Sarnak actually gave an explicit construction which has this property, which even loses this order n1 bound, or which loses this extra order n1 additive loss. It doesn't even have that loss. And since their construction, because they used some theorems of Ramanujan while proving this, since then, any graph which has this property is called a Ramanujan graph. So Ramanujan graphs are basically graphs which are exact. So Ramanujan graph, so any graph, Ramanujan is a family of graphs which has this property, but on the other hand, this is upper bounded by 2 square root d minus 1 by d. So if it has this property, Ramanujan graphs will have this property. It is upper bounded by this, lower bounded by this. It's almost tight. That's what a Ramanujan graph is.
Yeah. Thanks.
Okay. 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 So this is the Ramanujan graphs. What we will see next lecture. So far we have talked about them in an abstract sense. We talked about vertex expansion. We talked about spectral expansion. And we saw that if you have these things, they are useful in several sense. And random graphs have these properties. We will see explicit constructions in the next lecture. All of next lecture and more might be focused on explicit constructions. We will see some of them we'll see with proof and some of them we'll see without proof, these explicit constructions of graphs. What we will do in the next 40 minutes or so is try to understand random walks on expanders or just random walks in general.
So what does it mean to randomly sample an infinite family of deregular graphs? So like,
you're asking what's the probability distribution?
Yeah, something like that, yes.
Yeah, so the way you notice the way I have stated it here. So for every n, I pick a random graph on n vertices, which is deregular. And it says for that particular n, if you look at the probability, that probability is something it will be this statement. It will be this probability will be something like it will go as 1 minus, what do I mean by this? It will be 1 minus little o n1. So with high probability. So so for every n, we'll state this. It becomes a nice statement only when n is large enough.
Okay.
Is that okay?
Yeah.
Okay. So once again, we're given this random walk matrix M, which is a random walk matrix. We start off with some initial, say P naught is the initial distribution on vertices. This could be just possibly, it need not be the stationary distribution. It could be any distribution. It could also possibly a distribution just concentrated on one vertex. It's just put all its weight on a vertex, and then you begin taking a random walk on it. So you define P1 to be, so P1 to be, you take M transpose P0, and in general, PT plus 1 to be M transpose PT. So you take the sequence, you walk this way. This is a distribution walk, and the question we are going to ask is, does PT converge to the stationary distribution as P goes to infinity? And we will answer this question, say yes, if the matrix M has a spectral gap. Any spectral gap has a non-trivial spectral gap. Any spectral gap 1 minus lambda. As long as lambda is greater than 0, we'll show that this actually convergence will take place. Okay. And so what we'll do, we will show that actually the total, to show convergence, we'll understand the total variation distance between PT and pi. So what is the total variation distance? Total variation distance is just this. I'm just recalling the definition. It's half of summation B in V, PT V minus pi. It's the difference. That's for the total variation distance. And I want to ask, does this quantity becomes smaller and smaller as t goes larger and larger? That's what we want to ask. So let's slightly manipulate this quantity to a form which is more convenient to work with. So in general, we notice that when we're working with the random matrix M, it's nice to work things in which the expectation, it's not a summation, but it's sort of an average. The average is taken with respect to the stationary distribution. So I'll rewrite this quantity as the following. Just to, so that it's an expectation. So this is pi V PTV by pi V minus 1. This is in our notation, sort of the notation which we, so let me do one more step. So this is summation V in V, pi V. This is, if I look at pi inverse, pi is this, if you look at it, it's a diagonal matrix which had pi on its diagonal entries. Pi inverse PT of V, it's this minus 1. It's that quantity. And if you, this one, in keeping our notation, this is exactly half the, if you look at this, if this vector pi inverse PT minus the all ones vector, it is its one norm, but taken with respect to the pi distribution. And what do I mean by, in general for any vector, in general for any vector F, what do I mean by the K norm with respect to pi? It's the usual, this one, except it's the, so it's the usual thing in which you take the average with respect to K, you take FKV. I should take the absolute value. Okay. Okay. And take the 1 over the kth power of this. That's the second norm was defined that way. We are going to define every norm this way. So that's this quantity. Are people with me so far? Why am I doing this? Because in general, summations are not nice when I'm working with M. It's nicer to work with things which are pi norms. Things in which the averages, the summations is an average over pi rather than this one. That's the only reason for writing it this way. Any things so far? Are people comfortable with what I have done? It might be strange why I'm doing this. The only reason I'm doing this is things are nicer to work with pi norms when I'm talking about the random walk with respect to M rather than the summation, rather than the total variation distance, which is just a summation. I'm just rewriting it in a form which is more convenient to work with because I'm working with the random walk matrix M.
Is it clear pi inverse exists?
Pi inverse is a diagonal matrix. So if the stationary distribution puts its weight, notice the stationary distribution. What's the stationary distribution? It was a distribution which is degree. So as long as every vertex, as long as there are no isolated vertices,
Okay.
This is there. And if there's isolated vertices, you'll just throw it off the graph because the random walk doesn't influence that at all. So let's always assume we are working with the graphs with no isolated vertices. Okay. Okay. So this,
Need a
so this is
connected
the,
graph, right, for this.
sorry,
We
who,
need
what?
a connected graph.
What?
We would need a connected graph. Maybe my volume is low.
Yeah, we would need a connected graph, but what we would need a connected graph. We will eventually, so right now I'm stating it in general, but we would need the theorem. We will need a spectral gap firstly, and as long as the gap, and for the gap to happen, it has to be a connected graph.
Yeah.
Okay. And now the next thing which I'm going to do is the one norm is not the one norm is okay, but because you're working with inner products, the two norm is a better norm to be. We have a better handle on the two norm. So what I will bound the one norm instead by bounding the two norm. This is, I'll just use sort of this one, the norms only increase as you go. So this is smaller than the two norm. It is the norms decrease. Norms increase as k increases. This is an easy consequence of the definition of a norm. It's yeah. And what we will show that all of this initial manipulation was just to come to the two norm, which is a quantity I can work with nicer than the one norm. I want to relate the total variation distance to norm. So what we will show is in the next 10 minutes or so, we'll study how does pi inverse pt minus 1 2p 2 pi, how does that change when you take one more step in the graph? What happens when you take a step in the graph? This becomes m transpose. Let me first write down what it is. It's pt plus 1 minus 1 2 pi, which is exactly where pt plus 1 is m transpose pt. And this is what we'll try to study. We'll study how this quantity okay. Folks with me so far? Now let's write this vector pi inverse pt in the Eigen basis. So let's write it as some alpha times 1 plus a vector v, where v is orthogonal to the all ones vector into the pi norm. So I'm just writing it in this basis. It's some scaling of the first eigenvector and something orthogonal to this. Something which is similar to what we did in the expander mixing lemma. We have a vector, we are writing it in the along the all ones vector and its orthogonal component. Now I want to find out what alpha is. To find out what alpha is, let's take the inner product with 1 on both sides. So this is alpha 1 1. Fine. Okay. What is this? What's the right hand side? This is just alpha, the pi inner product. What's the left hand side? Notice this will just be summation. The inner product is pi v 1 with all ones vector, and again it's a pi. It's 1 by pi v because of pi inverse and ptv. So the way it has set up is such that the pi v cancel and you get just summation ptv. Therefore, all you get is which is 1. So alpha is 1 if pt is a probability distribution. All of this I'm stating that therefore pi inverse pt is equal to just the all ones vector plus some vector v, where v is orthogonal to the all ones vector. Okay. Notice this is a very nice quantity. So what am I looking at? Because we were actually interested in pi inverse of pt minus 1. This is the quantity which we really cared about. And this is exactly V. Okay. Now let's understand what happens. Let's understand what happens when we take a step in the graph. We take a random step. So that's just pi inverse. There you are looking at pi inverse pt plus 1 minus 1. This is by definition pi inverse m transpose pt minus 1. And here, this happens to be m pi inverse pt minus 1. This is because this is something which we saw, that m pi is equal to m transpose. Sorry, this is a statement which we saw in the very beginning of the lecture. This is a statement over here. It's this fact. Pi m is equal to m transpose pi. I'm just going to use this. This comes from the self-adjoint. Since pi m is m transpose pi, but this is m times pi inverse p transpose minus 1, because 1 is the value. What has happened now here? So this is mv. What did we need to do? We wanted to study this object. How does this object, the 2 norm of this object, change when you take a step in the graph? That is basically, I wanted to say, compare this to this. Now this quantity, the thing inside this, what the calculations first we saw, that was just a vector v, which is completely, v is a vector where and v is orthogonal to the all ones vector. Now this quantity, the other quantity, the next guy happened to be just mv. Therefore, this fact which we wanted to study, this one which we wanted to look at, pi inverse pt minus 1, the 2 norm of this versus the pi inverse pt plus 1 minus 1, the 2 norm of this. This is just v, the 2 norm of p versus the 2 norm of mv for some v which is orthogonal to the all ones vector. That's all it is. These two quantities are just these two. So it shrinks by a factor, and you know that m has spectral gap, this one. Therefore, and we know that for all, this is because m has spectral gap, because m has spectral gap 1 minus lambda. For all b orthogonal to the all ones vector, we do have that mv 2 pi is at least smaller than b by a factor of lambda. So each time it shrinks. All this is stating that each time you take a step in the graph, this 2 norm is shrinking by a factor lambda. So putting all of this together, we get that the total variation distance between pt and pi, which we upper bounded by the 2 norm this way, between 2 and pi, this shrinks by a factor lambda each single step. So this is, if I compared this to what it was in pt minus 1, there was a factor of this, the factor of lambda. So in other words, it's lambda t by 2 pi inverse p0 minus 1 2 pi. And that's actually the main takeaway of this one. You can find out what happens to all of this, but let's stare at this quantity. It says, look, let's stare at this. This is the final result which we have got. The total variation distance goes this way. Now notice that lambda is a number less than 1. Therefore, this is, as t is going larger and larger, this is shrinking. This is exponentially shrinking. So if lambda is some number less than 1, this is just becoming z. It's going close to 0 as t becomes larger and larger. And that says the total variation distance is going to 0 as t goes to infinity. And that's exactly what we wanted. We wanted pt to converge to pi. So as long as lambda is bounded away from 1, this quantity is going to 0 as t is going to infinity. Of course, if lambda is equal to 1, I don't know how to control this. This proof will not yield anything. And in fact, those proofs, you can show that in those cases, the graph will not mix. But if lambda, so this says that if lambda is any number less than 1, it doesn't have to be a constant bounded away, any number less than 1, then the total variation distance between pt and pi goes to 0 as t goes to infinity. So this says, as long as you have a spectral gap, as long as you have any spectral gap, anything less than any non-trivial spectral gap, the random walk will converge, and it converges to the stationary distribution. Are people with me so far? And this is just, there's some amount of manipulation I've done, but it's actually fairly simple. It's just, it almost follows from the definition. It basically is this fact, that is, you need to compare these two objects. And the only thing to notice out here is this is some vector v and this is some vector mv. So each time you apply m, this is shrinking by a factor lambda. That's all that's happening to the whole. Questions? Have I lost people? Do ask me questions.
So there was a graph, example graph that you gave in which the spectral gap was 1.
No.
So which means
yes.
Which means lambda is 0, right?
Yes.
So over there, it will converge in one step.
Yeah, but that's, you look at what was that graph. That graph is the graph in which every vertex is connected to every other vertex. So the moment
including a self loop,
you will get the uniform distribution, and this is exactly what it says.
Right. Okay.
Yeah. So if the gap were 1, that means that in one step you will converge to the stationary distribution, no matter how you start.
Right. Yeah.
Yeah. This is proving that's fact. It's proving something even stronger, that is gap. So let's look at what it is proving. So wanted to say a couple of more things. So let's look at, so this is the main theorem. This is the takeaway theorem I want to prove. That is the total variation distance is, so there is some initial gap. There's some initial gap which you start off because of the starting distribution. The starting distribution is P0. Because of that, this is some fixed constant, something. And because of that, and let's look at what this this is some fixed number. So because of that, you're constantly, and that is constantly shrinking as t keeps increasing. The total variation distance, larger t go, this is a fixed number, and that is shrinking by lambda to the t over 2, as lambda is a number less than 1. So this is going to 0 as t goes to infinity. So let's analyze this when the graph is irregular. Let's try to understand what happens. So let's try to understand star. So in the next 5 minutes or so, let's try to understand. So let's look at what is actually pi inverse P naught minus 1 to pi. The graph is deregular, therefore pi is the uniform distribution. I want to claim what is this going to be? The square of this is actually equal to summation over it's pi of it's 1 over n pi 0b times n minus 1 whole square. And let's assume you start. Let's assume the start distribution. The start distribution is concentrated on some vertex, on a vertex. That is P0 is of the form 0, 0, 0, 0, 0. Just one vertex, it's 1 and 0, 0, 0 elsewhere. So then what do you have? You have pi inverse P0 minus 1 to pi square root. This will be what? This will be summation, something like 1 over n. So there'll be just one vertex. There'll be just a, so this will be something like, it will be some order n. So this is the initial quantity you're starting off with. And then you're hitting it with, lambda to the power t. So what is known? So this is a known theorem. This, in fact, I think we're going to have it in the next homework. For any deregular graph, on n vertices, has spectral gap one minus lambda, where you want to write it this way, has spectral gap. I want to write it as spectral gap gamma, where gamma is at least 1 by some constant times dn square. That is, lambda is less than or equal to 1 minus cdn square. So the gap is so all I'm claiming is this is stating that any graph you take, the spectral gap is at least 1 over dn square. That's gap. Is all I'm claiming. Therefore, so that means lambda is less than or equal to 1 minus cdn square. So if you take t to be something like order cdn square times log n, then the total variation distance between pt and the stationary distribution is going to go, if you look at this quantity, this we saw was less than lambda to the t by 2 times this was some order n. This will go down to something like order 1 over, you can make it some order n to the 1 over 100. You can make the total variation distance go. Therefore, in other words, hence, in order cdn square log n steps, the random walk on any deregular graph converges to the stationary, to the uniform distribution.
So I got confused with this point.
Why?
Yeah, so for bipartite graph, it does not converge, right?
No, but lambda is bounded away from -1. So when I meant lambda, there's a gap on both sides, always.
No, but what is the statement? The statement you've written means that for any deregular graph, we have convergence. Do you have
If any deregular graph, so the statement over here. So any deregular graph on n vertices, which is connected and non-bipartite.
Yeah, non-bipartite. That's fine. Yes.
So I should mention this. Let me restate this whole theorem. This will this statement. Any deregular graph on n vertices, to take off the two extremes, that is connected and non-bipartite, satisfies gamma to be greater than 1 over CD n square. That is lambda is less than or equal to 1 minus 1 over CD n square. So modulo the proof of this lemma, what we have shown shows that any random walk on a graph which is connected and which is non-bipartite converges in polynomial number of steps. It converges to the uniform distribution. And this is just a consequence of this fact that we have here, the star inequality that we have here.
I didn't get why we had to add connected and bipartite in that theorem when we had stated that gamma is.
No, this lemma is not true otherwise.
So we also say that gamma is lower bounded by some 1 by CDN square.
Yeah.
So if it was not connected or not.
If it is not connected, gamma will be 0.
Yeah.
Not if it's disconnected, gamma will be 0. If it is disconnected, this gap becomes 0 over here. This is what I mentioned last time. If it are bipartite, this gap becomes 0 over here.
Right.
So I'm taking off those two anomalies and say once you take off those two anomalies, you will notice, not only will you notice it's not 0 on either end, but you will notice a small perceptible gap.
Right, so I was just confused because when we say that gamma is greater than or equal to 1 by CDN square, does it not exclude those cases already, like bipartiteness?
No. Yeah, it excludes, but then I want to state that any deregular graph has a particular spectral gap. So I can't prove this for every deregular graph, as Abhishek pointed out. I can only prove it if the deregular graphs were connected and non-bipartite.
Okay.
No. I'm not telling you the graph has this spectral gap. I'm telling you any graph. So any graph which is connected, if a graph is connected, this gap will not be 0. Okay.
Yeah, I got it.
Non-bipartite, this gap will not be 0. And I'm claiming that if both these gaps are not 0, they are not only not 0, they are actually some small inverse polynomial factor. That's all I'm claiming. The moment it's non-zero, it becomes a small, it is at least a noticeable gap. That's all this lemma is stating. Ishan, does it answer your question?
Yes, it is clear. I just got confused and I think I misinterpreted.
Yeah, certainly if gamma is greater than CDN square, it is certainly not, it is certain that implies it's connected and non-bipartite. But so I need to show, in order to prove that gamma is greater than CDN square, I need the fact that the gamma graph is connected and non-bipartite because of that. Okay, so this is stating, so what's the conclusion of what's the takeaway from all of this? And the takeaway from all of this is, the That is, a random walk in any deregular graph converges to the uniform distribution if the graph is connected and non-bipartite, and it converges in polynomial number of steps. Okay. But let's ask the remaining 5 minutes or so. What about random walk on expanders? So what's the difference between any deregular graph is connected and non-bipartite implies gamma is greater than or equal to 1 over some CDN square. That is, lambda is less than or equal to 1 minus dn square. What's the difference if you go for an expander which is deregular? Then gamma is actually larger than some constant c which is greater than 0. In other words, lambda is less than some 1 minus c which is strictly less than 1. Here you have a constant. The thing to notice is this is constant instead of being some inverse polynomial. Okay. So now let's apply the same thing for expanders. Let's apply the same thing for expanders. Here lambda is a fixed constant. It's something like, say, 1. It's bounded away from 1. It's like 9/10 or 99 by 100 or 1/4 or some such things. Something of that form. Then how many steps do you have to take so that this becomes inverse polynomial? Log steps. So notice this is polynomial of its own type. This is polynomial for any graph. This is like 1 over n, this is like n we saw. Now, if lambda is a constant here, therefore, if I take t to be some log number of steps, this will first be able to kill this one n over here, that is n, and furthermore it may. So all I want to say is that take a in an if an expander this, as the gap is as lambda is a constant bounded away from 1. Away from 1, order log n steps suffice to converge to the uniform distribution. So an expander mixes much faster than an arbitrary deregular graph. An arbitrary deregular graph, if you take polynomial number of steps, you will converge to the uniform distribution. That's what whatever we said over here shows us. But if you have an expander, then the spectral gap is constant and it mixes much faster. In log n steps, you will converge to the uniform distribution. And all of that is coming just from this inequality. This inequality over here, for an arbitrary graph, lambda is something like 1 minus some polyfactor. For an expander graph, lambda is a constant. It is like 1 over 100 or whatever. And that difference makes a big difference. How many steps t has, how large t should be before you begin converging. I'll just close the window. It's raining. So logarithmically, many steps are sufficient to converge to the uniform distribution in the expander. But polynomially, though for a general graph, it might be the case that you might require polynomially many steps to converge to the uniform distribution. For a general graph, which is deregular, connected, and bipartite and non-bipartite. And notice this log n is almost tight if you don't care about constants. What's the number of random coins in order to take an order log n step walk, starting from a fixed point. The first point is not a random point. What's the number of random coins you require?
Log D log n.
Huh? So
Log D log n maybe.
So in general, if this were t, it is t times log d.
Yeah.
So in other words, it is log n times log d, and which is order log n if d is constant. If you're looking at expander graphs where d is constant. That's the amount of randomness you're pumping in to converge this one. But notice, if you have to pick a uniformly random vertex, you need log n random points, because a uniform requires it's n bits of randomness, you need log n bits. This is stating that in order log n, which is not different, you start anywhere, you take a t step, an order log n walk, it does converge to the uniform. So this is almost, this is basically more or less tight. An expander converges to random walk. You start from a fixed point, just take a random t-step walk, where t is an order log n. You will invariably at the end of t steps, you will be at a uniform, more or less a uniformly random point in the graph. That's what we have shown. If the graph is an expander and the amount of random points you spend is basically what you would need to pick a completely fresh point at random, which is log n. This one. That's what this is. Notice with such few bits, you in a non-expanding graph, you will be very, very far away from uniform. You will not have mixed at all. Okay. I wanted to do one more thing. I won't have time to do it. Certainly, I don't have just a minute more. Would need half an hour more. But the main takeaway is this particular theorem. Is this fact is what I want to sort of emphasize on. It is the random walks converge. If there's a spectral gap, the random walk converges. The total variation distance goes to 0 as t goes to infinity. And it is at what rate does it go to 0? It goes at the rate of lambda to the power t, where lambda is the largest second eigenvalue, absolute second eigenvalue, and the smallest eigenvalue is that if you have a bound on that. So as long as you're not the complete, as long as you're not the disjoint graph, disconnected graph, or not a bipartite graph, this lambda is a number strictly less than 1. And in all those cases, you manage to get some form of convergence. And in those two examples, as we noticed, if it's a disconnected graph and or a bipartite graph, certainly there is no convergence. The random walk will never converge. In the disconnected case, you will never get out of the component which you are currently in. So you obviously won't go to the uniform distribution. And in the case of bipartite graph, every step, either you will be on the left side or on the right side. You will never, it will not convert to the uniform. Knowing the parity of the step, you will know whether you are on the right side or the left side. It doesn't go to your uniform random point. If you remove these two cases, this says a random walk converges. Okay. Okay. I'll stop with this. Any questions? Today was a very silent class. I don't know why. But
maybe because some of us saw this in toolkit.
that's possibly true. Yeah. So the main takeaway is this. So I'll just tell what we are going to do next time. So this time, what did we consider? We showed that random walks in expander graphs. So next time, I thought next time Ram Prasad will start lecturing, but I think I will take the first half of the lecture and then Ram Prasad will start, or the other way, where we'll do some distribution. What we showed today was random walks in expanders converge to the uniform distribution in order log n steps. Even if we start from an arbitrary fixed vertex. So it sort of says you start from a fixed vertex, completely deterministic vertex. Always start from the first vertex and you take a log n step walk. The final vertex looks like a random vertex in the graph, completely random vertex in the graph. What we'll show next time is, suppose you start with a random vertex. Of course, so you already have a random vertex. Now you keep taking steps in the walk. Every step will look uniformly random. You're starting with the stationary distribution, starting with the uniformly random vertex, take a step. We'll say that not only does each step individually in its marginal look as if it's random, but the entire collection of t steps also look somehow random. They might be dependent. They are steps in a walk, but yet they will look, so together they behave as if they are they will behave as if they are t independent vertices in a there'll be t independent vertices, not t steps from t consecutive steps in a walk. They will behave as if they are completely t arbitrary steps, t random steps, t random vertices in the graph. They will look like that. So next time what we'll do, we'll show the following is start a random walk starting at t step random walk starting at a uniformly random vertex has the property, and we'll formalize this, that all t steps look simultaneously random. It's not just each marginally looks random, but they all simultaneously also look random. And we'll formalize this in some sense. That will be the how we formalize this simultaneously random is what we will do next lecture. If it's a walk on an expander. Yeah, I'll stop with this. By the way, this is also something you would have seen, people who have taken toolkit would have seen, but then the constructions will be new. We will actually construct expander graphs in the next lecture. We will give an explicit construction. We'll not only give an explicit construction, we'll give a super explicit construction also. Okay.